All right, let's try example number 3 now from the handout that I gave you last week. This is a question that is much like questions you've already done, but a bit of an extension of it. Here we have two charges, and we want to find the electric field strength midway between those two charges. Let's draw it out here. We got a positive charge of 100 microcoulombs. Probably going to circle that in red to draw attention to the fact that it's micro, right? Not coulombs. We got to convert. To the right of that, we have a negative charge that's 75 coulombs. Once again, let's circle that to draw attention to it so we don't forget to convert that. The distance that separates them is 0.20 meters, or we could say 20 centimeters. We just have to convert it eventually. We're going to find the field strength right here, midway between. Now, what I want to do for this question is similar to what I did for those force problems where you had 3 charges in a row. It's not draw a free body diagram per se, because free body diagrams show forces. I want to draw a diagram that shows fields, but it's almost like a free body diagram, right? Let's pretend charge 2 isn't there right now. It's just charge 1. Charge 2 doesn't exist. Not right now, at least. Which way does the field point at point X as a result of a positive producer? Toward the producer or away from the producer? We know this, right? Are we toward a positive or away from a positive? The field always points away from positive. Now, what about the negative producer here? Charge 2. Well, the field always points toward a negative. We know the directions. Now we just got to find the values, the magnitudes, and add them up. Let's say E1 is KQ1 over R squared. That's our constant times the charge, number 1, which is 100 times 10 to the minus 6 coulombs, divided by, what distance am I going to use here? What's my distance? Yep, Philip? Good, 0.10 meters, because we want the distance to the midpoint. So we're trying to find the field strength, not from one charge to another. Let's pull out the calculator and do this one together here. We've got 8.99 times 10 to the 9 times 100 times 10 to the minus 6 divided by 0.1 squared gives us a value of 8.99 times 10 to the 7. That's newtons per coulomb. Now let's find the value of E2, the electric field caused by the second charge. My charge is 75. It's negative 75, but we always drop that, right? My distance will once again be 0.10. Eight 8.99 times 10 to the 9 times 75 times 10 to the minus 6 divided by 0.1 squared. 6.7425. Now what do you got to do? 3 words. Add them up. Positive or negative? What about this green one? Positive or negative? Why? Somebody said it. It does matter. Sorry? No, in fact, we don't want to make them opposite because they're both in the same direction, right? So you could make them negative, technically, although I'm not sure why you do that, but you could as long as it's the same sign, right? Odds are you're probably going to make it positive because you're going to make the other one positive because they're both to the right. Does that make sense? All right, so let's say 8.99 times 10 to the 7 plus 6.7425 times 10 to the 7. When we add those up, we get 8 point, that's not right. Add that to 6.7425. 1.57 times 10 to the 8. And it's positive, so it means it's to the right. Now, if one of those had been to the left, and it could have easily been to the left, could be in another question, we just add them up, but add a negative to it instead of a positive. It's almost the same thing as that Coulomb's law with 3 charges, except we've only got 2 charges, and we're dealing with fields, not forces. Okay, what I'd like you to do right now at your desks is try question number 8 on worksheet number 8. You're going to have question number 9 for homework as well, but number 8 I want to give you a chance to work on in class here, and then we'll go over it in just a few minutes once you've had that chance. All right, time to do number 8 as a group here. It says 2 charges in a straight row. The first charge is a value of positive 5 times 10 to the negative 5. So here we go with the first one. 5.00 times 10 to the negative 5. Here we go with the second one. It's over off to the right. Its value is negative 2.5. So we're going to draw that as a negative value. Negative 2.50 times 10 to the negative 5 coulombs. Now the distance that separates them is 4.5 centimeters, or we're going to make that 0.045 meters. We want to find the field strength once again midway between. Now let's look at the field caused by the positive. Fields always point which way relative to a positive? Toward or away? Going to point away, right, Cody? Going to point away from the positive. So we're going to draw that green field to the right, away from the positive. Now what about the blue one? The blue one's caused by a negative. The field always points what? Toward or away from a negative? Towards. So we're going to draw that blue one to the right as well. Both of these fields are to the right. So what we need to do is calculate both of them. When we do, we're going to find that E1, that's the one caused by the positive, is 8.879 times 10 to the 8. What would be the distance that I would use there for R? Yep. Good. Half of 45 centimeters, or 22.5, which is 0.0225 meters. Good. So we calculate E2 the same way, same distance actually. KQ, drop the sign of the charge, divided by R squared gives us a value of 4.44 times 10 to the 8. Now, of course, these are both positives, so when I go to find the net electric field, I'm going to add them together, right? And when I do both positives, I get 1.33 times 10 to the 9. And the answer would be to the right because both fields are to the right. Right plus right equals right. All right, I'm going to leave you with number 9 to work on for homework. I'm going to go a little bit further with the electric fields now and introduce a new kind of electric field. Last week, I showed you that the electric field surrounding a positive producer looks like this. I showed you that in the review today as well. The electric field surrounding a negative producer diamond would look like this. These are both what we call non-uniform electric fields. We call them non-uniform because the electric field strength is varying depending upon location. The electric field strength right here is greater than the electric field strength right here. The closer you are to the producer, the stronger the field, and we can recognize that by the density of the field lines. Right? The closer the field lines are together, the stronger the field. Further they are apart, the weaker the field. So we're going to see these are both non-uniform fields, which means the field varies with location. Versus what I'm about to show you, which is a uniform field. I'm going to draw 2 charged parallel metal plates. Now this is an idealized situation, a perfect situation. We can have things that look like this when we don't have charged metal plates. I'll give you a couple examples of that in a moment here. But for now, just go with this. So we got two plates that are charged. One's positive, one's negative. There will be an electric field between those plates from positive to negative. These field lines are parallel to each other, which means the field does not vary with location. The field strength right here is exactly the same as the field strength right here. This is a uniform field because the field is the same everywhere. Now, when would you see one of these uniform fields where the field lines are parallel to each other in real life? Yeah. Okay, it could be. Yeah, it could be. I'm thinking of a really, really obvious one, actually, though. One that's not, in the basement, up in the ceiling of the basement of your house. One that's not hidden in the walls of your house. How many of you guys went on the field trip to West Edmonton Mall last year? On the field trip we took to the amusement park last year, where did you see two charged metal plates? No? Good guess, though. The bumper cars, right? The floor is metal, the ceiling is metal, and what do they have joining the two of them together? This thing going up from the bumper car, right? Which completes a circuit. There's an electric field between those two plates. One plate is positive, one plate is negative. An electric field, a uniform electric field that goes from the positive plate to the negative plate. Where else have you also seen it? Here's a situation where it's not actually metal plates, but it's like two metal plates. Here's a cloud and here's the ground. When the cloud becomes negatively charged and the top of the earth becomes positive by induction, then we would get an electric field pointing upwards from the ground to the cloud. Now, the earth is rounded, right? But over a relatively small area, the earth is essentially flat. And because the earth is essentially flat over that small area, it's like the earth is a bottom plate and the cloud is the top plate. And it's a relatively uniform electric field in between. In other words, the electric field strength right here would be the same as the field strength here, which would be the same as the field strength right here. Okay? Metal plates or things that are like two charged metal plates with the field lines parallel to each other creates a uniform electric field. Now, let's go into the math, because the math is going to be a little bit different for this than it is for what we've been doing up until now. Let me give you the first equation again for an experiencer. This equation, E is equal to F over Q, applies in this situation if I have a non-uniform electric field, as long as I have something right here or anywhere else experiencing that field. If I have an experiencer, then I'm allowed to use this equation in a non-uniform field. Now let's draw our uniform field. Let's make it a top plate positive, bottom plate negative, field points downward. I'm allowed to use that same equation with a uniform field as well, as long as I have something experiencing the field. So in other words, nothing changes. When you've got an experiencer, you use the experiencer equation, regardless of whether you've got the old field that we learned about last week or the new field, this uniform field that we just learned about a few minutes ago. Still use this equation. If, however, we look at the second equation that we learned last week, that's the producer equation, it's valid here. We've got a producer that produces a non-uniform electric field. But what about here? That equation isn't valid for this because that second diagram for parallel plates is a uniform field. This equation is only valid for a non-uniform field. So the first equation, use it as you did, and now you can use it in this new context as well. The second equation, use it as you did, but you can't use it with this new stuff. You can't use it with the parallel plates. If we can't use the producer equation for parallel plates, then we got to come up with a new equation that is like a producer equation, but for parallel plates. Let's say the non-uniform producer equation is what you see up there now. Let's come up with a uniform producer equation. This is the one that's good only for parallel plates, only for uniform electric fields. In other words, if I have a non-uniform field like this, like I had last week and like I had earlier on today, I cannot use this new equation for it. But if I have my parallel plates or something that's like parallel plates that approximates a uniform electric field, then I can use it. Now, delta D stands specifically for the distance between the plates. It's not how far apart a charge is from the top plate or how far it is from the bottom plate. It's not how far a charge has moved. It is always the distance between the plates. This distance right here. Delta V, this is kind of a tricky one here. Delta V stands for the potential difference between the plates. That's going to be measured in volts. Potential difference between the plates is the difference in energy per coulomb of charge between the plates. What does that mean? The difference in energy per coulomb of charge between the plates. Say there's 25 people in this room, okay? We have $100 combined. We have $100. Let's say money is energy. Okay, money is energy. So how much energy do we have? $100, right? We have an energy of $100. My potential is not my energy. It's not the amount of money. My potential, which is given by the symbol capital V, is the money per person. It's like energy per coulomb. Okay, energy per coulomb, money per person. What's my potential here? My money per person if I have $100 with 25 people? 4. My potential is $4. That's what it was, at least. That's what it is right now, at least. But when we go down to 7-Eleven and everybody buys a Slurpee, Pepsi, not dark, runny Slurpees, because I like the light, icy Slurpees, just so you know. Light colored icy Slurpees. Our potential then becomes $2.10. This is how much money we had per person before we bought the Slurpee. This is how much money we had per person after we bought the Slurpees. Pepsi, icy, lighter colored ones, because those are the ones that I like. What's my potential difference? The difference in energy per coulomb or the difference in money per person? It would be 190. So potential difference is not energy, right? The $100 is the energy, but it's related to the energy, right? It's not even the energy per coulomb, because that would be the $4 or the 210. It's the difference in energy per coulomb or the difference in money per person. So my last equation, delta V over delta D, is the potential difference or the difference in energy per coulomb divided by the distance between the plates. Remember, it's only valid with a uniform electric field. I'm going to write those three equations again on the board. KQ over R squared, that's my producer equation for a non-uniform field. E is equal to F over Q, that's my experiencer equation. And then this new one that I just learned, E is equal to delta V, the potential difference, divided by delta D, the distance between the charges. I'm going to circle the top two equations. Now I'm going to circle the bottom two equations. This is called a Venn diagram. It shows things that different equations have in common. These top two equations in my Venn diagram are used when we have a non-uniform electric field. In other words, if I've got something that looks like this, or maybe it's a negative producer, whatever, it's a non-uniform electric field. The bottom two equations are used when I have a uniform electric field, when I have two parallel plates or something like two parallel plates, the cloud and the earth, whatever the case may be. That middle equation I can use whenever I want, as long as I have something experiencing the field. So my producer equation for a non-uniform field, my producer equation for a uniform field, in my experiencer equation, that's good for either uniform or non-uniform, as long as I have something experiencing the field. Example number 4 on the handout that I gave you last week says a potential difference of 20 volts exists between two charged parallel metal plates. Potential difference, this is the difference in energy per coulomb of charge between the two plates, 3 centimeters apart. Top plate is negative, bottom plate is positive. What's the magnitude and direction of the electric field? Well, the direction is pretty easy, actually. The top plate is negative, bottom plate is positive. An electric field always points from positive to negative, away from positive toward negative. So the electric field is pointing upwards. Well, what about the magnitude? Well, I know something about the producer, but it's a uniform field producer, parallel plate producer. So we're going to use the producer equation for parallel plates. 20 volts divided by 0.0300 meters gives me 666.6667 coulombs. What is it? Newtons per coulomb? What other units could I use for this? Look at my equation. What other units could I use for this now? Yep. Volts per meter. They're both exactly the same thing, so use whichever one you want. Keep using newtons per coulomb if you want, or use volts per meter if you want. They're interchangeable. That's not too bad. What about my second problem here? What's the force experienced by a proton if it was between the plates? Listen, we've used the producer equation for parallel plates. We can't go to this one because that's for a non-uniform field. The only other option we have is the experiencer equation, so let's try that. Let's say E is equal to F over Q. The experiencer equation, let's rearrange that. F is equal to Q times E. We're going to say 1.60 times 10 to the minus 19 times the electric field. Volts per meter equals, what's my value there? I get 1.07 times 10 to the negative 16 newtons. The electric field was pointing up. It's a positive particle, so the force would be pointing upwards as well. And the last question, this one should be pretty easy for us now. The acceleration, we're just going to say A is equal to F over M. Just solve for the force. You got the mass. Divide the two. Okay, your homework for tonight. Worksheet number 8, questions number 9, 10, 11, and 12. 9 to 12.